Welcome back, ladies and gentlemen, to another Tidbit of Words production here on the Drunken Science channel. Today I wanted to show off a piece of software that I've been developing over the past couple weeks during my winter break and college. So I'm an environmental science student, and I study lots of subjects in the environmental science field, including geography, GIS, biology, botany, and so a lot of my side projects and passion projects are inspired by those. I also really love math and programming, so this piece of software is where those two passions of mine have met. So the goal of this piece of software is to simulate the evolution of flowering plants. So right now it's in the early stages of development. I have a very basic working model, but a lot of the work that I've put in up till now has not really been focused on the actual model for the plants, the ecological model, or getting very specific about like water, precipitation, temperature. I just said water and precipitation twice. Like water, temperature, pressure, nutrients, carbon, things of that nature. This current simulation does not have those in it, but the goal is to provide a simulation framework so that I can focus on the model and make it really easy to represent and simulate using evolutionary algorithms. Now, what is an evolutionary algorithm, you might say? It's an optimization problem optimization method inspired by natural selection. So let's see if we can kind of, instead of blabbing on about it, I think the best way to go about it is to just kind of show it off here, and then maybe we can dive into some of the few specifics a little bit later. So first off, I'm going to hit this new button up here. I'm going to create 250 little flowers. Now each of these flowers, if I can click on one over here, if you look over here, has a total height. It has an energy usage rate, an energy production. It has a leaf area, so it has petal area, root area, and a whole bunch of other parameters that I'm not displaying in this little window right here. So when I click on this new button, the computer randomly generates all of these different parameters for the flower. So we can consider these parameters its genome, and each of these parameters determines some of these calculations, or the phenotype, if you will. And we're abstracting phenotype a little bit here, but that just really makes our lives a lot easier. So the goal of this simulation is to find the best fit flower and see if they'll survive. So in this current simulation, if you look over here, we have this fitness category, or over here in this this little window we have fitness. So when I run the simulation, is going to calculate fitness. And in this current simulation, fitness is purely based off of the total amount of energy that the flower has and the total amount of water that the flower has. So total energy plus total water. If at any point during the simulation the flower's fitness falls below 0, it dies and it gets removed. So I'm going to go ahead and I'm going to change the simulation speed on with this slider up here just down a little bit. I'm going to go ahead and hit start, and we can already see a bunch of the flowers not surviving the initial. I don't even know if there'll be any that will survive this initial run. We have this one. We have this one little dude right here, flower YCT. Come on, buddy, you can make it. Oh nope, he died. All right, so let's see. Maybe if we create a few more flowers this time around, maybe about 1,000 flowers. I'm creating 250 every click. We usually get some flowers that'll survive. Yeah, so there's 72 right now that are surviving. So let's talk about some of these other parameters that we're looking at. So right here, there's time step, and there's also this evolve counter limit. So whenever the time step reaches 500, the simulation is going to stop. It's going to take the top four flowers in the simulation as far as fitness goes, so the best fit flowers, and I'm going to go ahead and pause this just for a second so I can explain. It's going to choose 1 flower, 2 flower, 3 flower, 4 flower. So it's going to take the top 4 parents and it's going to have them produce offspring. So it takes half of the genome from one parent, half of the genome from the other parent, splices it together in a crossover event and makes a new kid. And then this kid generates all of its phenotype from its parents' genome, and then that kid gets put out into the world. And it starts out with 0 fitness, and then as the simulation runs, it has to calculate its energy and water every single time step. And if it survives, it survives. If it doesn't, it doesn't. So this is one of the key points of a genetic algorithm or an evolutionary algorithm. We have a population of solutions, these flowers. We calculate their fitness. If they survive, then we choose 2 parents. We cross over their genes, have them produce a kid. We have a small chance of maybe tweaking one of those parameters called mutation. That's also very important. Helps us avoid local minimums or maximums in this hill climbing optimization problem that we're going for. And then we put those kids back out in the solution space and we rerun the problem, the sequences steps all over again. I'm going to go ahead and start the simulation now, and I'm going to go ahead and run it a lot faster. So in this simulation, each of the different seasons gives the flowers a different amount of energy or water. So summer, spring, and fall, we're given energy, we're giving water, and then in the winter time, we're taking water away and we're taking energy away to simulate cold temperatures and lack of incoming solar radiation. So I don't know if we'll be able to see it in this particular simulation, but what happens every, about 5 years or every 500 flowers or so, which I can change in these parameters over here, is we'll stop the simulation, we'll take the best performing flowers, the top 32 performing flowers over the course of the simulation. They don't have to currently be in the simulation. They can have died, but their information gets saved. And then we also take 20 random flowers, and then we kill all the current flowers off, put those randomly selected 30 best flowers and 20 random flowers into the simulation and restart it all over again. Now this is kind of the final step in the genetic algorithm. So we create a whole new solution space based off of the previous one. We run it. We do it over and over and over again. And then hopefully over time, only the flowers with the traits that are suited to survive in this environment will have children and survive and make offspring. And slowly over time, our fitness will go up, which is essentially the fitness equation is the equation that we're optimizing in this simulation. So I hope that gives you a nice overview of the application that I made. Like I said, a lot of the time is spent making sure that it runs smoothly, like being able to make these windows pop out, getting all these sliders and buttons to work properly so that they do the things that I want them to do, getting these labels to update in real time. There's just a lot of really specific things that you have to do when making an application to make sure the machinery under the hood works. Now, where I'm going to be focused on in the future is really on the model, the flower model, changing these parameters, incorporating temperature, precipitation, nutrients. Look, there was one of those generation events. And you can always tell generation events because the best flowers cluster around themselves because the way that I had it programmed, and they don't randomly get chosen in a new spot. Their XY position is close to their parent. So that is really interesting. They're all almost up to 4,000, 5,000 fitness now. So really the next goal over the course of the next 3 or 4 months is to really optimize and program all of these natural relationships that lots of really smart people have observed of plants and their environment into the simulation. And hopefully once I get enough complexity programmed into this piece of software, I'm not going to tell the flowers what is the best working flower or what is like the most optimal angiosperm type plant in the world. All I'm going to do is program in all of the natural relationships that we have observed in the world, and then hopefully what we'll be able to see is some of these flowers mimicking some real life plants that we have out there in the world, as far as like height, number of flowers, number of petals, when do we decide to bloom, when do we decide to send out our seeds, how do we decide to send out our seeds. All these different types of choices and phenotypic expressions are something that I'm really interested in programming and giving these flowers a chance to show off. All right, well, I hope you all enjoyed this video. If you have any questions, comments, suggestions, feedback, I would love to hear it down in the comment section. You can also email me at tidbitofwords@gmail.com. I'm really, really excited about this project. It's a passion project of mine. I don't really have to do this for any assignment. And I really am looking forward to the next couple months and seeing where this will take me. I hope you all have a wonderful day, and I will see you in the next video.